Hi everybody, welcome back to Under the Integral Sign. Okay, so today we're going to be proving our first integral formula. And we will be using the Leibniz rule for differentiation under the integral sign to prove this formula. Take a look at my proof on the Leibniz rule for differentiation under the integral sign so you know where this all comes from. Because I don't believe in using formulas that you don't understand, so definitely check out that video. I will link to it in the description. It's going to show you why this process works. Anyway, we're going to be developing a formula for this integral right here for a and b greater than 0. That means our a and our b have to be greater than 0. All right. So the first thing that we're going to need to do to calculate this is to evaluate our function of a and b at the point a is equal to b. So basically, we just replace a with b anywhere we see an a. And that's going to give us this. And of course, that's going to equal 0 because we just have something minus the exact same something right here. That's 0. 0 over anything is 0, and the integral over any interval of 0 is 0. So f of b is equal to 0. Okay, we're gonna use that later. The next step is to differentiate our function of a with respect to a. Now this utilizes the Leibniz rule for differentiation under the integral sign, which I derived in my very first video on this channel. So f prime of a is of course equal to the derivative with respect to a of this function right here. And we're calling this a function of a where b is an arbitrary constant. So you can see that this will be a function of a, depending on what arbitrary value for b you choose. Okay, well that's going to be equal to the integral of the partial derivative with respect to a of the integrand. Again, I proved this all in my last video, so check that out, definitely. You want to know where this stuff comes from. All right, so we're going to compute that partial derivative. Now remember, a partial with respect to a, that means that anything that is not an a is treated as a constant. Things that are not a in this thing include x and b. So x and b are simply constants, which means that this negative e to the bx over x drops out in the differentiation. So the only thing that we're really taking the derivative of is e to the negative ax over x. Now, if you take the derivative of e to the negative ax, you will, of course, get negative x times e to the negative ax. The x's will cancel, and you'll be left with nothing but this. So that is our partial with respect to a. Okay, so that means we can replace this with this. And we do that in the next step. So the derivative of f of a is simply negative 1 over a, because this integral right here easily evaluates to negative 1 over a using techniques that you would have learned in Calculus 1. Okay, so our f prime of a is equal to negative 1 over a. So now it's pretty easy to find what f of a is going to be equal to. We just have to anti-differentiate our f prime of a, right? Okay, so our f of a is equal to the integral of our f prime of a, which we know is negative 1 over a. So that's equal to negative integral 1 over a dA. All right, well, that's going to give us negative natural log a plus c. So now we need to figure out what our c is. And we can do that by, remember, at the beginning of the video, we found that f evaluated at b is equal to 0. So that means that 0 is equal to negative natural log b plus c, implying that c is equal to natural log b. So we just substitute that back into our f of a, and we get that f of a is equal to negative natural log a plus natural log b, which, using the properties of logarithms, simplifies to natural log of b over a. All right, so that's it. Since our f of a was the integral we were trying to find, and of course we're calling it a function of a and b, where b is an arbitrary constant when we're actually evaluating the integral. But in any case, this integral right here, as long as our a and b are greater than 0, evaluates to exactly natural log b over a. All right, guys, I hope you enjoyed that, and we will see you in the next video.